Good morning, everyone. Thank you for coming to John's defense. Some of you were definitely at Auckland's defense on Monday, and you'll notice that the introduction I have for John kind of parallels that. The only main difference at the beginning is that John was born and raised in New York, but then he later went to Princeton to study chemical engineering, and then received an offer from Stanford to pursue his PhD in material science. In October of 2009, like Ashwin, he sent me an email expressing interest in joining my group. And I'll just, again, read you a few more excerpts. Dear Dr. Dionne, I know that Ashwin has been in contact with you to discuss your research. He and I both attended Princeton together as chemical engineering majors. It turns out they were roommates as well. Is that right?
No.
Oh, you weren't roommates. Yeah, we were both chemical engineering majors, so we have similar backgrounds and also many of the same interests. He has actually forwarded me the articles you sent to him, which we have both read. I have 3 years of funding through an NSF fellowship, so hopefully that will ease some of the burden on you as a new faculty member. I was like, did this guy just copy from...
It's not coordinated.
So, as you know, I had invited Ashwin to join me for a day of experiments at Berkeley, and I also had John join that day as well. And from reading the emails and seeing their backgrounds, I thought they were probably the same person, or at least very similar personalities, that they convinced me that they are totally different in their approach. Whereas Ashwin was incredibly enthusiastic and excited. Here's the evaporator, and he'd be like, oh, that's so cool. John was a little bit more reserved in his enthusiasm. And I think the story that I remember the most when I think about those early days with John is when we were at Berkeley, and my friend and collaborator Matt Sheldon and I were trying to make a single semiconducting nanocrystal solar cell. So to make a single nanocrystal solar cell, you have to deposit nanocrystals on a substrate, find one, and then lithographically make contacts to it, whether it's a Schottky type contact or an ohmic type contact, and then once it's made, you have to do the single nanoparticle electrical and optical characterization. And John asked me, how long does it take to make a single nanoparticle solar cell? And I said, well, now we've optimized the process where we can make it in 1 day. And I was so excited that we had made it in 1 day. And John said, it takes that long? I was like, oh, geez, this guy is incredibly well suited for graduate studies. But I decided to take him into my group, and it's a decision I certainly don't regret. I guess, as many of you know, John is very introspective and an incredibly deep thinker. I had written in my introduction that he rarely smiles, and in fact, when walking over here with John Fan, John said, oh, is John your first student? I said, no, actually my second. And then, we were just talking about how awesome you were, and then John Fan said, he rarely smiles. And I was like, oh. But I think, in part, that's because you're never quite satisfied with your own work, and you're always trying to find ways to improve both your work and yourself. There are a few times when he has smiled. The first is when the editor at Nature suggested that he turn his letter into an article. So he was like, oh, maybe that means the editor is going to accept it. And I was like, John, of course that means The second time he smiled that I actually caught on camera, that was a blurry image, was when he won the Gold Award from the Materials Research Society, a pretty significant accomplishment for a graduate student, particularly one who was only in his 4th year. And hopefully he'll be smiling very big this afternoon when he will finally be the official Dr. Scholl. So with that, take it away, John.
Thank you, Jen, for the introduction. Good morning, everyone. Thank you for coming to my talk. Today I'm going to be highlighting some of the nanoscience research projects I've been working on in Jen's group. Specifically, I'll be discussing how the plasmonic properties of metal nanoparticles change as their dimensions shrink into the quantum size regime. So one of the core drivers of nanotechnology has been the emergence of new material properties as the dimensions of the materials shrink to the nanoscale. A very visible example of this is the optical properties of noble metals. Take, for example, silver. We're very familiar with its gray metallic color, but if we shrink it to nano size in the form of nanoparticles of different shapes and sizes, we see that it can actually support a wide variety of colors. These colors are due to a phenomenon called plasmon resonances, which is studied in the field of plasmonics. While plasmonics as a field has really taken off in recent decades, we've really been using this phenomena for hundreds of years. For over a millennia, artists have been coloring glass using not organic pigments, but actually incorporating metallic salts, which ultimately form into metal nanoparticles. And so, in effect, these were very early nanotechnologists, although they didn't really understand the science behind why these were displaying the colors they do. Today, our understanding is considerably better. So let me walk you through some of the basics of plasmonics. Let's take one of the simplest plasmonic systems, a silver nanoparticle. It's in 10 nanometers in diameter and is a sphere. Because due to its metallic nature, it has a sea of free electrons, conduction electrons, which when you shine light on it can collectively oscillate, and this is called a surface plasmon resonance. And so these electrons can oscillate back and forth as the light is incident upon it. We can understand these resonances in very small particles, which are substantially smaller than the wavelength of light, through their polarizability. This polarizability equation is dependent on the radius of the particle, the permittivity of the particle itself, as well as that of its surrounding medium. These could then be implemented in the scattering and absorption cross-section to determine how this particle will resonate and at what frequencies. So to kind of just walk you through a very simple example, let's take this silver nanoparticle in a vacuum. We want to see where it will resonate. Well, based on this permittivity function, we want to make this denominator as small as possible. And so that's when the permittivity of the particle is equal to -2 times its surrounding medium. We can find this on the permittivity function for silver. And we see that's around 3.5 eV, which indeed, that's where the resonance occurs. So we could further tune where this resonance, with resonance energy, the particle exhibits this phenomenon by altering its size. It's causing a shift in the resonance. Its shape, such as making it longer into like a nanorod. And finally, by changing the surrounding medium, going from a vacuum into water also causes the resonance to shift. Another interesting aspect of plasmonic resonance is that they're able to concentrate light into very small sub-wavelength volumes at the nanoscale. These are called Muirfield Hot Spots and have potential implications for potential applications. For example, one can use it for cancer therapy. So you could take gold nanoparticle shells and incorporate them into the body where they'll selectively attach onto tumor cells. These gold shells resonate at infrared frequencies, so one could use an infrared laser light, which will pass harmlessly through the body, but once it reaches the nanoparticle, it will cause it to resonate, forming these hotspots, which will then photoablate the nearby cancer cells. Another potential application is for chemical sensing of the surrounding medium. So we have a gold prism, which resonates very strongly, and it is very sensitive to its local environment. Nearby, we have a palladium nanoparticle, which is absorbing hydrogen. During that process, the refractive index of the palladium is changing, and the gold is able to sense this by modifying its resonance frequency, and so that can be detected optically in the far field. Finally, another application is to do very sensitive molecular detection. So by incorporating plasmonic nanoparticles, such as these 2 gold nanospheres, in between the 2 nanospheres, you have a very strong near field, which enables us to do molecular detection at very small concentrations and greatly enhance the sensitivity. So these example applications in the field of plasmonics as a whole has generally focused on particles which are greater than 10 nanometers in sizes or have gaps between the particles and feature sizes greater than 1 nanometer. And with these dimensions, they can be very well described using classical electrodynamics. But we were interested, what would happen if we pushed this one step further to even smaller dimensions? What new phenomena would we observe at the smallest of size scales? And this is actually a very important consideration. For example, in industry such as Intel, which is manufacturing microchips and is greatly decreasing the dimensions of all of its transistors, we're already at 14 nanometers in feature size and continually getting smaller. Quantum effects are now playing an ever greater role, such as quantum tunneling. So it's going to play a major role in the design constraints of designing these chips, but it can also enable brand new applications. For example, it could be used for atomic sensing, such as through scanning tunneling microscopy, which makes use of electron tunneling to actually do atomic scale imaging, such as at IBM, they've been able to do atomic scale movies. And it also can enable new devices, such as quantum confined structures, such as quantum dots in LCD display. So for today's talk, I'm going to be talking about 3 different plasmonic systems that have their dimensions shrinking to the quantum scale. The first of which is a single particle system, which has particles less than 5 nanometers. Second will be 2-particle system with a very small gap in between. And third will be a 3-particle system, which also has very fine gaps. So let's start with the first single particle. So why was I interested in single particles? One thing that particularly interested me is that there are emergent catalytic properties when you make noble metal nanoparticles very small. For example, if we take gold, which is usually chemically inactive at larger size scales, as you shrink its dimensions down below 5 nanometers, we start to see this emergent catalytic activity, such as oxidizing carbon monoxide into carbon dioxide. We thought potentially we could study these plasmonic nanoparticles, gold is a plasmonic nanoparticle, and be able to monitor these chemical reactions in situ on the single particle level. However, doing so optically is actually quite challenging. The scattering cross-section of these particles as they get very small decreases very dramatically, and it's been extra challenging to be able to observe single particles at the smallest of size scales below approximately 10 nanometers. So instead, the community has been looking at ensemble measurements, kind of taking a collection of these particles and looking at them all together. So in this case, they were able to synthesize a relatively monodispersed collection of nanoparticles ranging in size from 18 all the way down to 2 nanometers, and were able to get an absorption signal from them. However, studies like this suffer inherently from heterogeneity in their samples. As the particle size gets smaller, you can see that there is some distribution in the particle dimensions. And so these heterogeneity effects will really kind of obfuscate what is the fundamental processes that are going on. There's also the influence of organic ligands in these systems. So to synthesize these very monodispersed particle sets, they had to incorporate a lot of organics, which potentially could be chemically damping their surface and affecting the resonance. That may be part of the reason why some other studies were actually seeing different trends as particle size decreased. So in this first case, we're seeing that the resonance energy redshifts or goes to lower energies as the particle size decrease, but other studies, such as silver particles in glass, they actually increase very slightly in their resonance. So I was really interested to get to the bottom of this, really understand fundamentally what is going on at the small size scales, and really design a very controlled experiment that could eliminate as many variables as possible and get to the heart of the matter, like how do resonances change at the very smallest scales. So first, I would like to work with a synthesis that does not involve organics so that we eliminate that chemical damping. Second, I would like to be able to correlate the size, shape, and spectra of individual particles to get rid of that heterogeneity effect. And finally, develop a theoretical model to be able to explain these results that we're collecting. So for the first step, I found a synthesis that does not involve organics to make these particles, and it just uses sodium borohydride as a reducing agent and stabilizer, so we can synthesize a variety of sizes of particles all the way down to 1 to 2 nanometers. Second, instead of using optical detection techniques, which we saw are quite limited for single particles, instead we use the great transmission electron microscopy facilities we have here on campus. So using our Titan TEM, which has an imaging resolution less than an angstrom in high resolution aberration correction mode. And if we instead work in a STEM mode, which is scanning transmission electron microscopy, where the electron beam is focused, we still have a resolution that is sub-nanometer. We could take very nice images of these particles. We can then combine this with a spectroscopy technique called electron energy loss spectroscopy, which enables us to get quantitative information about the plasmon resonances in these particles. So the way it works is that you have your focused STEM electron beam, you shine it right next to the particle. The energy of that electron that's passing by the particle is decreased very slightly when it excites the plasmon resonance in the material, and that slight decrease in energy is detected through a magnetic spectrometer prism, and it can be recorded. This technique actually has a further added advantage over optical detection techniques in that by selective placement of the electron beam, you could actually excite particular modes, plasmonic modes in the system, some of which could not even be observed optically. So let me walk you through a relatively simple example that's a well-studied system. Classically, it has been observed optically, and that's a silver nanoparticle. It's 20 nanometers in diameter. So we see from our EEL spectra that we collect that we have a single resonance. This occurs around 3.3 EVs, which will correlate to theoretical predictions and optical measurements. And so we see that indeed that is the surface plasmon resonance expected for a single silver nanoparticle. If we now move the beam slightly over into the bulk of the material, we see a new resonance appear. This actually corresponds to the bulk plasmon resonance in the particle, which actually has a different geometry of its mode. So rather than kind of a sloshing back and forth, up and down of the surface resonance, and now you have a kind of breathing mode in and out. So this, due to its symmetry, would not actually be able to be excited by light. So we're seeing new modes that hadn't been seen in optical techniques. And now moving the electron beam further into the center of the particle, we can change the relative intensities of these modes. So moving forward, now that we have this great technique, let's try it on the smallest of particles. So using particles that range all the way down to approximately 2 nanometers in size, we're able to collect their EEL's spectra. Kind of looking at them all in aggregate, we see that as the particle dimensions decrease, that we actually see below 5 nanometers a rather substantial increase in their resonance energy, or blue shift. It's about 0.5 EV or so. So how do we explain this blue shift? Traditionally, theorists over the past few decades have theorized what the resonance of very small particles would look like, although they hadn't really seen them at this individual and very small particle size level. They speculated that as the particle dimensions decreased, the electrons that are excited in the material would actually encounter the surface more frequently, and so as they're bouncing around would actually have more scattering events, which would lead to some dampening of the resonance. This is this gamma term, which is a function of the Fermi velocity over its radius. So as the particle gets smaller, the dampening gets greater. And while this does a great job of predicting that the resonances do, in fact, dampen and get diminished as the particle size decrease, it actually predicts a very slight red shift in the resonance. But we saw a very substantial blue shift. So how can we explain that? So instead, I turn to a quantum type approach where we believe that as the particle size decreases, we can no longer use kind of classical approximations for these materials. So rather than have a continuum of density of states of the metal, that actually the energy levels start to become discretized, and you actually start to have quantized energy. So you can have, for intraband transitions, you could have specific discrete energies for excitations going from occupied energy levels to unoccupied. So implications after incorporating this into an analytic model, which modified the permittivity of these functions. So we see that the permittivity actually changes as a function of particle size. So this ultimately resulted in, indeed, a very distinct blue shift as the particle's dimensions decrease, as well as the dampening that we were seeing. So putting it all together, so we can take our theoretical analytical model, which again predicts as the particle size decreases, that we have a distinct blue shift. We can overlay our experimental data, which actually has very nice agreement. And finally, we can compare this against classical predictions indicated by the white dotted line, in which we're seeing there is, in fact, a very substantial deviation, about 0.5 EV or a 15% alteration. So while our model was relatively simple, we wanted to further validate it with more rigorous models. So this was an ab initio density functional theory model, which goes all the way down to first principle calculations with quantum mechanics. They also determine how the permittivity function would change as a function of particle size. So they were able to generate the permittivity function of a couple nanometer diameter particles, and then through their calculations extrapolate these out to larger sizes. Was then able to use these extrapolations to also create a scattering profile for these particles at different sizes. And we see, again, it's showing a very distinct blue shift and a very similar magnitude and agreeing very well with our experimental data. So some takeaway messages from this first part. We've seen that STEM EEL's technique can now really surpass optical detection techniques for very small nanoparticles, enabling us to both image them and also collect spectra from them. It also allows single particle observation, and for once finally conclusively determining that there is a blue shift in the resonance of these particles at the smallest sizes. We were able to use an analytical quantum model to modify the permittivities of the silver, which also generated a very similar blue shift. And so from these findings, we see that since there are such dramatic changes at very small sizes, this will really influence the design of future plasmonic systems using particles less than 5 nanometers. All right, moving on to two-particle systems with very small gaps. Why are we interested in two-particle systems? Well, they actually enable another degree of freedom for designing plasmonic systems. Because if you bring two particles very close to each other, their plasmon resonances will couple and start to be altered. One could design potentially new optical tunable antennas. So the closer you bring these particles, the more the resonances will shift. You could also synthesize these particles using DNA strands to connect them. And so this could potentially be used for detecting molecular biological processes. Finally, as I mentioned earlier, if we bring two particles very close to each other, you can achieve a very intense electric field in between them, which can very substantially enhance the sensitivity for spectroscopy techniques such as Raman scattering. This potentially could enable all the way down to single molecule detection. Traditionally, it's been speculated that as you bring particles very, very close to each other, their resonances will continue to shift to lower energies, and the intensity of the fields in between them will just continue to asymptotically increase in kind of an exponential fashion all the way down to infinitesimally small distances between the two. However, more rigorous quantum calculations have recently been performed, again using density functional theory, which actually start to disagree. So this dipolar mode, which is that very strong resonance mode in between the particles, is predicted to, at approximately 0.5 or so nanometers, start to decrease in intensity and become quenched and no longer continue that redshift to lower energies. And indeed, due to these calculations, they speculated that at separation distances around 0.5 to 1 nanometers, the intensity of that field will be maximized. So the community was very excited about this and wanted to actually experimentally prove and see what are the true limits of plasmonic resonance shifting and the intensity in these fields. However, to do so has been experimentally quite challenging. You could take a top-down approach to fabricate these particles using techniques such as E-beam lithography. However, due to just inherent technological limitations, these are generally limited to gap sizes around 5 nanometers or greater. Another technique would be to use DNA self-assembly or other chemical separators in between these particles. But again, the separation distances are minimized at around 1 to 2 nanometers or so. And recently, with such interest, there's been kind of an arms race to get all the way down to the very bottom and smallest of size scales. And so there's been a number of high-profile works, including some with somewhat grandiose titles, such as Probing the Ultimate Limits of Plasmonic Enhancements. In these studies, in the study at bottom, they use self-assembled monolayers to separate a particle from a film. At top, they used improved E-beam lithography tricks in order to get all the way down to 0.5 nanometers. But in both cases, the separation distances, the small separation distances that they were able to achieve were approximately 5 angstroms, or 0.5 nanometers. So this is really still missing that key quantum regime. So I really wanted to try to be able to explore at the very, very smallest of size scales. So again, I'd like to design a very controlled experiment where we study individual dimers and be able to correlate their geometry and spectra and be able to observe the modal evolution, how these resonances are changing as the particles get closer to each other. So ideally, we'd have the exact same particles and just move them closer to each other. And then we wanted to compare these experimental results versus the classical theory as well as the new quantum theory. So how are we going to do this? Through my time on the TEM, I've been adjusting a variety of the parameters, such as the substrate we're looking at particles, the particle chemistry itself, and the intensity of the electron beam. And what I found with the proper combination, one could actually cause particles to move around on the substrate. And you'll see that one's about to be eaten by the other one or kind of merged together. So I thought, can we use this in a more controllable fashion to actually fabricate structures at very, very small size scales? And indeed we can. Using a kind of focused electron beam with very controlled dosages, we can actually cause particles to get closer and closer to each other and ultimately merge into a single entity. So the electron beam energy is sufficiently intense that you can actually cause the particles to recrystallize and form into a single entity here. So now we've seen we can move these particles with the focused electron beam. Now we can also collect their spectra at these different separation distances. So let me walk you through kind of a basic experiment looking at how the resonances change as these particles get very close to each other. Let's start with two 10 nanometer particles with a 3 nanometer separation gap. We shine the electron beam as indicated by the red dot, and we collect a single spectra. So this resonance is approximately at 3.3 EVs, which, if you might remember from before, is the same resonance as a single silver nanoparticle. So this indicates that these particles are not interacting with each other, that they're effectively not coupled, they're too far apart. However, now we can use the electron beam and cause these particles to move closer to each other, and now we're starting to see new plasmonic modes emerge. So what are these plasmonic modes? So we really had no way of telling unless we could do theoretical calculations to really observe the shapes of these resonances. So working with a postdoc in our group, Aitzel Garcia-Chari, he's an expert on using a classical electrodynamic simulation technique called boundary element method calculations. And so in these very rigorous classical technique, you can actually incorporate an electron beam and match the geometry of our system exactly, and thus match the modes that we're seeing exactly, and generate field maps where we can actually see the path of the electrons moving in our system, or the electric fields in our system. So we can identify that at the lower energy resonance actually corresponds to a bonding dipolar plasmon. And in this case, we actually have the two dipoles in the particles aligned. So we have these all lined up, whereas at higher energies, we have a bonding quadrupolar plasmon, which is just a little bit more complicated system with additional nodes. So we have plus minus charges as such. Once the particles start touching, we have new modes start to emerge. So this at much lower energies. Again, using classical simulations, we can predict what's happening. And so we observe that you have emergence of a new mode called a charge transfer plasmon. Effectively, these particles are now acting as a single entity, and so you have a single dipole for the entire length of the particle. And then again, we also have another higher order charge transfer plasmon mode with additional nodes. It's somewhat analogous to the gap mode, but now the particles are attached. What's interesting is that as these particles continue to merge, you start to see this blue shift in the resonance of the lower energy charge transfer plasmon until ultimately it's approaching towards a single resonance, and since the particle itself is now slowly approaching towards a single sphere again. So we're all the way back to where we started. So using these great classical electrodynamic simulations, we can actually predict the modal behavior at every separation distance, from positive separation between the particles as well as negative separation distances where they're effectively overlapping with each other. Comparing this against our experimental data shows that these predictions actually do quite well in simulating our system. It's only at the very smallest size separations that we really start to see a divergence. So I'll zoom into the very small size regime. So at this very small size gap, as I mentioned earlier, it's classically predicted that as the particles get very close to each other, this bonding dipolar plasmon resonance will continue to redshift and remain quite intense. And then once the particles are touching, the charge transfer plasmon will be very strong. However, our experimental results were not agreeing with us. So let me explain how we would do a measurement at these very, very small size scales. We have to do a continuous collection of EEL spectra as the particles are moving. So we start with taking a picture. Particles are around 0.7 nanometers apart. Then we collect spectra from these particles continuously as the particles are approaching each other. Then take another picture, collect some more spectra, picture, spectra, etc. And so now we have a full set here, and we can compare these, the modal evolution between the classical and our experimental data. We see that in contrast to the classical simulations, the bonding dipolar plasmon does not continue to redshift and remain very intense as the particles are merging. Instead, it actually starts to become quenched at at several angstrom separation distances. And the charge transfer plasmon does not emerge very strongly, but actually somewhat weakly before intensifying. So we can compare these against the density functional theory calculations I mentioned earlier. So plotting them in a similar fashion, using surface plots, we can see in their case, they were simulating 4 nanometer sodium spheres, which are qualitatively similar to our silver system. And indeed, they were seeing that their bonding dipolar plasmon resonance actually also gets quenched at positive separation distances prior to the particles touching, and then the charge transfer plasmon also emerges somewhat weakly before intensifying. So based on this agreement, since this model incorporates quantum tunneling, whereas the classical model didn't, by analog, we can see that our system most likely is indicating quantum tunneling in our experimental system. So some takeaways from the second part. We saw that we can use the STEM EELS technique to not only image the particles, collect their spectra, but we can actually move them as well. This is now allowing the fabrications of structures with very small gap sizes below 0.5 nanometers. And this is enabling experimental observations at these small size scales and observing quantum effects. And really showing the limitations of classical theory and the necessity for quantum theory at these very small size scale. All right, final section. So 3-particle systems. So why are we interested in a 3-particle system beyond the logic of just 1, 2, 3, the next possible logical choice? 3-particle systems are actually quite interesting that they support a wide variety of new modes. Among these are an electric dipolar mode, a magnetic mode, and other more exotic dark modes that cannot be detected optically. So in this electric dipolar mode, it's actually similar in shape to the bonding dipolar plasmon resonance, that you have this kind of alignment of the dipoles. In the magnetic mode, you actually have a circulating displacement current, effectively forming a circle here, which enables a magnetic mode, even though the particles themselves are non-magnetic. And then finally, you have a dark in-plane mode, which, due to the directions of these dipoles, actually would not be excited by light. Of these modes, the magnetic mode is actually of particular interest in that it can be excited at optical frequencies. So what can one do with an optical frequency magnetic resonance in addition to optical frequency electric resonances? Well, one could actually start to create metamaterials, which with the combination of these electric and magnetic resonances, one can tune the refractive indices and actually realize some exotic material properties. A second application potentially would be to enhance chiral spectroscopy. So it's quite important in the community to be able to distinguish between enantiomers, or molecules that have the same chemical formula, but actually have a symmetry based on kind of right-handed, left-handedness. So in the biological community, they've been able to develop a drug, such as S-thalidomide, which actually treats morning sickness in women. But if you accidentally get the wrong enantiomer, such as R-thalidomide, it actually induces birth defects. So to be able to actually detect the relative concentrations you have of these two different enantiomers is actually very important. And so through using plasmonic systems which have very strong electric and magnetic resonances, you can actually enhance this the relative chiral signal from these particles. And it's generally been found in these proposed applications that you want these resonances to be as strong as possible. You want the electric and magnetic coupling to be very strong. And so that generally requires as close gap sizes as possible. However, experimentally realizing very small gaps in the trimer system, like the dimer system, has been quite challenging historically. So again, using top-down electron beam lithography, they've been able to achieve gap sizes around 5 nanometers or so. Using colloidal self-assembly techniques, again, around 1 to 2 nanometers, such as the work done by John Fan here. So it's really unknown what happens at the very smallest of size scales when you bring these metamolecule type trimer structures into the quantum regime. So again, very controlled experiment. We want to study individual trimers and be able to directly correlate their geometry and spectra. We want to be able to excite, in this case, excite distinct modes in the nanostructures. Because we're dealing with a system that has a much more complicated variety of modes, we have to be very selective in where we shine the electron beam. And then we want to observe the modal evolution as these particles converge with sub-nanometer gaps. So first, I need to synthesize these trimer systems. To achieve actually a detectable optical magnetic resonance, you actually need to work with slightly larger particles than we've previously been doing so. So I had to work with a synthesis that was able to develop relatively monodisperse, approximately 20 nanometer diameter silver nanoparticles. These have a very light coating of citrate on them, and when they're deposited on a TEM substrate, they actually self-assemble into a variety of shapes. It includes dimers, trimers, other higher-order multimers. But since we're doing kind of single particle or single system studies, we can just search around on our TEM grid until we find the particular trimer system we were interested in and then conduct our experiments. To study this trimer system, we can place the electron beam in a variety of locations. Based on our simulations, we found 3 locations would be particularly useful for detecting the different modes in the system. At the vertex, at the edge, and at the center. For sake of time, I'm really only going to talk about 2, the edge excitation and the center excitation. So we take our electron beam, excite it at the edge of this trimer system. We get our EEL spectra, which indicates we have 3 distinct peaks here. We again turn to classical boundary element method calculations to determine what are the nature of these modes. And we see that the spectras generated is also matching quite nicely. Looking at the field plots for each of these different resonances, we see that for the magnetic mode, at the lowest energy, we see the magnetic mode, which has that circulating displacement current. The next higher energy mode corresponds to the electric dipolar mode. And finally, we have a collection of higher order modes that are somewhat degenerate and kind of all land on top of each other. So the system becomes quite complicated at that point. Looking at another excitation location in the particle system, we shine it in the center. And we see that effectively we only have one single mode, which actually agrees very nicely with our classical simulations. And based on these simulations, we can see that this indeed is the dark mode, the orientation of the dipoles as such. Now we can take these particles and start to decrease the relative gap sizes. They start at around 1 nanometer or so, and then cause them to ultimately merge into a single entity, and then we can collect spectra on them while this process is occurring. We found a particularly interesting trimer set through our studies that actually goes from a 3 separate particles to ultimately one that has 2 connections, so it's kind of a V shape. And then we collect the EEL spectra during this process, going from bottom to top. We can first compare this against classical theory to understand this modal evolution. So you might see that there are some similarities between these spectra, but there's also actually some notable differences. But first, let's walk through. This is a relatively complicated system. Let's walk through what each of these resonances represent. So again, at this lowest energy, we're seeing this magnetic mode with the circulating displacement current. According to classical theory, they would believe that as the particles get very small gap sizes down to 0.1 nanometers, that this magnetic mode would continue to be present, it would redshift and become even stronger. Second, we have this electric bonding mode, which again, as the particles get closer to each other, would just continue to redshift and remain quite strong. And then we have these higher order modes, as mentioned earlier. Once the particles are actually touching, we get a new magnetic mode. Instead of having 3 different gaps, now we just have 1 gap, and so it's at lower energies. We have a charge transfer mode, kind of similar to the dimer case, except now we have 3 particle systems, so the particles are merging along here and here. And then finally, other higher order modes, which are similar geometry to the gap modes. So let's compare this against our experimental data again. We see that there are some similarities. The higher order modes remain constant throughout the entire process. We see the emergence of a magnetic mode here and here, the emergence of charge transfer modes here and here. But instead, we see in our magnetic mode, for our experimental results, we actually see this diminish in intensity and it no longer continue to redshift. And the bonding electric mode does not continue to redshift at all, but it actually starts a very slight blue shift prior to the particles actually touching. So we want to simulate this quantum mechanically. However, these previous density functional theories, very rigorous quantum mechanical simulations, cannot be done on such a large size scale. We're working with 20 nanometer particles. Each of them have hundreds of thousands of electrons in their system, whereas density functional theory has generally been limited computationally to around 1,000 electrons or so. So instead, we would like to modify classical theory, but through some heuristics, we can actually simulate the effect of quantum tunneling without having to do the full quantum simulations. So working with some collaborators in Spain, they developed this quantum corrected model, which actually modifies the permittivity in between the particles to actually simulate the conductivity due to quantum tunneling between them. They were able to validate the system by comparing against density functional theory for, again, these 4 nanometer sodium spheres. And so we see actually very nice correspondence with the quantum corrected model and the ab initio density functional theory. And both of these actually disagree quite strongly with the classical theory, where you see this continuous redshift prior to particles touching. So working with these collaborators, now we're expanding the applicability of this quantum corrected model to a 3-particle system. And so we just received this data very recently. And what we've seen is that it actually agrees with our experimental data quite nicely. So again, we see this magnetic mode in our experimental data start to become quenched. Here, also, the magnetic mode disappears at approximately 0.3 nanometers. In the bonding electric case, also, we have a blue shift, again, seen in the quantum corrected model. So it appears that the quantum tunneling is indeed playing a substantial role in the evolution of these electric and magnetic resonances at the very smallest of size scales. Just kind of wrap up, we actually looked at different modes in this system. So this is exciting that dark resonance by shining an electron beam in the middle until it actually becomes a single merged entity. What we see is that the resonance more or less remains exactly the same throughout the entire process, which agrees quite nicely with boundary element method classical simulations. So in this case, classical simulations are sufficient to be able to simulate our system. And why in this case is quantum not actually influencing the system, whereas it did in the electric and magnetic case? Well, it's actually due to the orientation of the dipoles in the system. Due to their geometry, they're actually inhibiting the electron tunneling between these particles. So without tunneling, classical simulations do great all the way down to the smallest of dimensions. So some takeaway messages from this third and final part. We can now use STEM eels to also selectively excite different plasmonic resonances in these particles. And we see that for certain resonances that they are indeed affected by non-classical effects, quantum effects, whereas others, such as like dark mode, classical simulations are perfectly fine at every separation distance. And we see that these non-classical effects, these quantum effects, are actually well predicted by new quantum corrected model simulations that have been developed. So, some final conclusions. Hope I got you a little excited about this new STEM eels technique where it's ever expanding. We can do high-res particle imaging, we could do spectral analysis, we could do selective excitation of the modes, and even move the particles around to fabricate new structures. And so by using these newly developed techniques, we can now observe quantum phenomena that hadn't been observed before. This includes in single particles, we can definitively say that they are blue shifting and their permittivity is actually being affected at the very smallest of size scales. And for dimers and trimers, we can now conclusively look at the quantum tunneling between these particles. So all of these effects are going to be really influential in designing these kind of plasmonic structures at the very smallest of dimensions. So that concludes my talk. I'd like to do a few acknowledgements before I open the floor for questions. So of course, I'd like to thank funding sources. I'd also like to thank our collaborators. So I'd like to thank Eileen, who trained me on how to use that Titan TEM. It's a very complicated piece of equipment, so I thank Eileen for being so patient with me over all the years. I'd like to thank Eitzel, who performed these classical boundary element method calculations. He really expanded my understanding of plasmonics and really was instrumental in understanding what we're seeing in these EELS systems. I'd also like to thank our collaborators in Spain. We've been working with them very closely over the past few months, and they've really done a great job working on this quantum corrected model, so now we can understand even these complicated quantum systems. I'd like to thank our committee members. I really appreciate you taking the time out to come to this. I realize how busy you guys are, since even 3 months out, it was really difficult to find one day that all of you guys were in the country at the same time. I've really enjoyed all of your classes, and I've learned a lot. It's really helped me develop as a material scientist or reading your papers. So I'm really looking forward to our discussion in the closed session. I'd like to thank Jen. She's been a really great advisor, and her enthusiasm is so contagious, as you can see in this picture. We do this pretty much every day. We just like stand around looking at files. Jen still has great lab skills, so yeah, you've been really inspirational to all of us, and I'm so glad that I took the risk of joining a brand new lab group, as it was really paid off. Speaking of which, I'd like to thank all the dionne group members. Most of you are in the audience right now. It's been great working with such a bunch of really fun and smart people. I've really enjoyed all of our conversations in the offices, some of which, very serious scientific conversations, and some of which are not so serious and not so scientific. I'd like to thank my other friends I've met here at Stanford. It's really enriched my time here over the past 5 years, from material science friends or Princeton alums, hiking buddies, and from music groups. It's really been such a great experience being here at Stanford. Of course, I'd like to thank my girlfriend, Michelle. She's been such a great support over the last 3 years we've been together. We've had so many adventures already, and I'm really looking forward to more adventures in the future. Finally, I'd like to thank my family. You've been such a great support. My interest in scientific research, even since all the way back to high school when I was doing science fairs. I thank you so much for supporting my decision to do a PhD. And particularly, I'd like to thank my 2-year-old niece and nephew, who are my biggest cheerleaders. Fortunately, they couldn't be here as they were at a conference. So with that, I'll pull up my conclusions, and I'd be happy to take any questions that you guys have. Thank you.